So when we talk about the ecliptic, we're talking about the tilt at which the sun appears to each observer, right? Because it does its progression annually from season to season, and it moves from tropic to tropic, it actually gets higher and lower. And it is that path that appears to us to move within a 23.4 degree gap of our azimuthal grid, or our local alt-az grid. So if you look at what the sun does, we typically think that they're moving around and they're intersecting. But when we're talking about eclipses, we're talking about much more than the frequency at which these two circles intersect, because they're also in 3D on a different path. The sun's at this slight ecliptic path, about a 5-degree tilt, and the moon's a little bit off of that, as you can see. So because of this intersection, the rate at which they actually intersect is much less, right? So otherwise you'd have an eclipse every month. Ecliptic is the sun's tilt from a base level that we observe in our grid. It goes from here to here. This is the 23.4 degree gap that we notice, that we observe in the sky, right? From the sun's precession. But if we look up to what the sun is actually doing, as it goes from tropic to tropic, it's going higher and lower. See, it starts off really high, the Tropic of Cancer, goes really low to go out to the Tropic of Capricorn over here. So what that looks like to us, of course, is the sun progressing in this band, right? All above and beyond. So the observation is this, and then they contrive it back to get a ecliptic at which the whole solar system is actually tilted at to make sense of the sun's angle and parallel light rays. So they take this observation of this 23.4 degree band with which the sun migrates, and then they created a whole model that said the solar system is actually tilted at this angle and that all light is parallel and it's actually at a balanced flat axis, but the whole solar system is tilted 23 point or whatever. So when we're talking about eclipses, we're talking about when these two intersect. These would be the nodes, which we can see here. These are the ascending and descending nodes. These are Rahu and Ketu, and these are the intersection points at which they actually intersect. What the sun's ecliptic was compared to the moon's track, how they're at different inclines, and how those separate inclines mean that the intersection is much less frequent when talking about the eclipse cycle, the lunar cycle, and the great astronomical year. Here's a nice animation. We're going to watch an eclipse from beginning to end. And we're going to see that these little knots above the solstices and the equinox, but we're going to see the nodes pop up, also called Rahu and Ketu. And when the moon and the sun intersect at one of these nodes, if it's at the ascending node, then it has a solar eclipse. If it's at the other node, then it's a lunar eclipse, right? So this is a different interpretation of a syzygy, where the heliocentric model would have to say the alignment of the sun, moon, and the earth, right? But in our world, it's just an alignment of the sun and the moon in a specific order, and that there's sort of a reverse syzygy, in which case the moon is at the opposite node, and that's how you get a lunar eclipse, right? So if the intersection points appear to move forward as the sun, we're jumping forward from the sun, giving it the appearance of moving backwards, right? Because we're progressing time fast, as we did in the beginning. And when we're looking at the sun and the moon here, when they're going to intersect, now we see a node finally, right? So if the sun and the moon meet at opposite knots, a lunar eclipse happens. So if the sun and the moon are here, if they meet at the same knot, a solar eclipse happens. So if the sun's over here and the moon's over here, lunar eclipse. If they're at opposite nodes, if they're at the same node, solar eclipse. I thought that's one of the coolest observations about this. Right? What's dynamically causing a lunar eclipse is that the sun's always at a specific offset to it. We should look into that with our magnetic polarization and offset fields from the Faraday effect that we were talking about before. Probably something happening there. Here is from the observer's position, right? How an eclipse would occur. This specifically was one back in 2017, and it was for this observer in, looks like, southern US. And of course, as the sun and the moon progress around, they seem to align to the observer. And that's why there's a specific band at which the eclipse occurs, because they only occur for each observer, because it takes into account the perspective at which you would see them intersect. go into, I think, the explanation of the Saros cycle and some lunar periodicities. So we'll just hop right into this part, because these lunar periodicities are going to be the backbone of predicting eclipses. It's how, this lunar cycle works every 18 years, how the same conditions realign to occur for the same type of eclipse. And then that same eclipse will occur 3 times. And then when it recurs on itself again, it's called an excelligimus cycle, which is
sounds like something out of the Harry Potter movie.
Yeah, really, like Expelliarmus, bro.
Just cast a magic spell on us.
It's when it's 3 cycles of 18 years, so that the one eclipse that would be oscillated 30 degrees around the world would then occur back on the same spot. I kind of butchered that, but we'll go into it for sure. We're going to watch how I explain eclipses using these 3 periodicities, and then we're going to watch how my heliocentric buddy Steve explains the very same thing. And we're going to look at similarities and difference in an aim to see, is eclipse prediction heliocentric or geocentric? But essentially, these are the components, right? What is the Saros cycle? It's that synodic, or when the synodic, draconic, and anomalistic months intersect and repeat, which means the moon's lunar cycle, the moon's position, and its ecliptical orbit, and when it eclipses the same node. That's what all 3 of these mean independently, but we're going to go into those individually real quick right now. How solar and lunar eclipses occur. The Saros actually arises from a natural harmony between 3 of these periodicities. So the synodic month, the animalastic month, and the draconic month. So let's define them first. The synodic month, the time between 2 successive new moons corresponding to the moon's orbital period relative to the sun. What that means in reality is the luminosity of the moon, which is directly correlative to the sun's position, right? Because the further the sun gets away from the moon, the brighter its luminosity becomes. The closer the moon gets to the sun, the lesser its illumination becomes, right? So the synodic month is the timing of this periodicity. Its mean length is something like 29.53 days. The animalastic month is the interval between 2 successive passages of the moon through perigee, right? Remember, in an elliptical orbit has perigee and apogee, perigee being the closest, apogee being the furthest point in its cycle. The animalastic month then is the interval between 2 successive passages of the moon through its closest point. And then its mean length is 27.55 days. Then you have the draconic month, which is the period between 2 consecutive passages of the moon through the same orbital node. So remember, we talked about Rahu and Ketu and the lunar nodes. Well, this periodicity describes the time it takes for the moon to go from one node and then all the way back through the same node again and again. The mean average is 27.21 days. Notice they're all close, but all a little bit different, and they do line up ultimately. So let's break up what makes up an actual Saros cycle. Well, within the Saros cycle, you have, again, the synodic, draconic, and animalastic months. So again, synodic, moon returns to the same phase. Draconic, moon aligns with the same node. Animalastic, moon returns to perigee, the closest point. After one Saros cycle, or lunar cycle, to 18.03 years, these 3 inner periodicities realign almost perfectly, creating similar eclipse conditions. So, the lunar cycle is 18 years, 10 or 11 days, and 8 hours. Now, why? Why is it that long? Well, it's 6,585.32 days, or 223 synodic months, or 242 draconic months, 239 animalastic months. The extra 10 to 11 days account for the lunar distance around the Earth, and the 8-hour offset means that eclipses in the Saros series shift westward by about 120 degrees longitude between each cycle. Now, longitude, of course, having to do with time, because the hour angle transformation to convert longitude to right ascension just means 4 minutes per degree, meaning that it's just the time component of the celestial system, which equates to the longitude, which is the angular separation on the graticule. So it is this 8-hour offset actually that determines the shift. If it was not for this 8 hours, the eclipse would occur exactly where it did before, and we'd have an ever repeating cycle. Because of this shift, it means it occurs at a slightly different place each time, and that is what sets off the cycle. And that means that it's happening in a different spot in the zodiac each time, and its track around the cycle will create the greater celestial cycle that we're talking about. Depends on whether the first eclipse of the series occurs east of a rising or a falling node, and which of the two nodes that the moon is crossing when it's on the ecliptic. And that determines the direction in which it shifts by 120 degrees, right? So it takes about 18 years for the teams of eclipses that make up this cycle to make a 360 around our realm. That is its cycle, right? So the 651 or 649 great astronomical year is a 2 revolution cycle. It's got 2 revolutions of one cycle of 325 years and then another cycle of 326 years alternating. And of course, each one of these has 18 times 70, which would be 1,261 eclipses in each cycle, pairing or Saros cycle. After one Saros, the moon will have completed roughly a whole number amount of synodic, draconic, and animalistic periods, and the sun-moon geometry will be nearly identical. That means the moon will be in the same phase at the same node, and it'll be from the same distance at the same spot, almost. So the same eclipse happens every 18 years for a total of 36 times in 651 years. So that's a grand eclipse cycle of 651 years contains something like 2,520 eclipses. So and that is the chronometer with which we will use to date our civilization.
We'll start real quick with how it repeats, right? We went through how it moves 120 degrees westward, right? So this is the amount of longitude. Here's our heliocentric lad explaining the same thing, how these periodicities align to the Saros cycle, the same amount. And it says, hey, each time it occurs, it'll be this much further west, right? So that's the result of that 8-hour leftover, because of course the stars precess around flat Earth according to sidereal time. So if you give it 8 hours, it occurs a third of the way around the world, right? Because the stars have moved that much further. Now, what this looks like is you get a repeating cycle of eclipses. So this eclipse right over here has this shape, occurs in 2117. 18 and a half years later or so, it occurs the same eclipse, same shape. 18 years later, a third of the world offset, 120 degrees offset. Now 18 years again, same eclipse, same shape, shifted a third of the way around the world, right? So this happens in 2117, 18 years later in 2135, 18 years later in 2153. That is how the heliocentric model characterizes eclipses. They use this Saros cycle, which is why they're spread out between thousands of years, because each one is within 18 years. So they're only characterizing those of similar characteristics, and then they're lining them up into these big, long Saros cycles in which they tell the user almost nothing, right? The other thing is that they separate them into solar and lunar chronologies, and the texts are completely different, even though the characteristics they use to predict each are the same, with slight variations. And so these, again, are all 3 different types of eclipses. This eclipse over here, again, is happening 2171, 18 years later, same shape, 2189, shifted a third of the way around the world, and then 2207. And when this eclipse happens a 4th time, and it happens right back where it started, that is what I was trying to say earlier, extelegimus cycle, right? That's when that lines up. That's 3 Saros cycles lined up. Now, if we were to picture what that would look like, right? We have sort of the sun and the moon at a different offset. As the moon aligns, it doesn't intersect because it's at a different height as we were looking. That's why only every 606,583 days does it align with what we just showed there, right? So it's because it's weaving up and down every month, it's not going to hit the sun to cause an eclipse. So if we were to graph out what the difference would be, right? We have the spinning sidereal stars around the flat Earth. And again, if you were to wait 8 hours, and the same eclipse that happened over here would then happen over here, would then happen over here, would then happen right where it started, right? That's what the 8-hour difference is, roughly a third of a day. If you were to take a series of eclipses, and to map them out, you would start like this: Series 1, Series 2, Series 3, Series 4. They'd occur like this. We're on 5 now. We're on 6, 7 around the world, 8, because they have partners and they always appear in pairs. And this is going to go up to all the way to 18. And we've completed one whole circuit. Now, this is the same characteristic of eclipse happening and happening and happening as it shifts and rotates and shifts around the world. Now, just for fun, we're going to ask a heliocentric lad to explain most of what I just explained through his interpretive framework. And we're going to see if it's very different from what I just explained, all right? So we're going to ask my friend Steve over here. Steve's, well, I'll let Steve tell you. I got some questions about eclipses and the eclipse conditions and how and why eclipses occur. Do you have any qualifications that would help you to answer some of my questions?
Hi, I'm Steve Bleiler. I'm a professor of mathematics and statistics at Portland State University.
Yeah, all right, Steve, that's cool. Seems really complicated to be able to figure out when and how the next eclipse is going to happen. And there's a lot of people that seem convinced that you need NASA and heliocentricity and mass attracting mass and gravitational predictions with the three-body problem to predict it. Do I need any of that in order to predict eclipses?
It's really just the sort of mathematics that you learned in grade school and an understanding of what we in music would call harmony. When is it that various tones, frequencies line up with each other?
All right, so then how would I start to do it? Would I need to get some spreadsheets? Do I need to get a big canon of eclipse predictions from NASA? Do I need a giant tomb? Do I have to buy a special eclipse book from the Mayans? Or what do I do to start?
You can start in your backyard with a conveniently placed a pole, maybe a tetherball pole or maybe a light pole across the street, and a good timepiece so that when things are happening. And if you have the same place to sit every night, you can pick a celestial object like the sun or the moon or a bright star or one of the planets, and you just time when it goes by that pole. The other thing, if you have some way to measure angles, protractor or even just two pieces of wood with a single nail stuck between it so that you can measure the angle between the horizon and the object you're looking at when it goes through past your pole. That's all you need to do.
Oh, numbers, those numbers. Oh, I see. So we're going to have to use like the heliocentric mass of the moon calculated from the angular size formula based on an optical diameter of 0.53 degrees and Newton's law. We're not going to have to use just Kepler's law. We're going to have to use the heliocentric math, I bet, right? Is that what you're going to say?
Basically, you get that knowledge by just sitting in your backyard and looking at the heavens.
What?
It's totally free. And again, all you need is a vertical stick, a reasonable timepiece. That can be the two bright stars in the bucket of the Big Dipper, which actually form a giant clock, and a place to sit. And you just need to know where something is once, and then some time later when it reappears there. That gives you how fast its apparent motion is in the heavens, and that's all you need to know.
Oh, so you're saying all I need is an observation and a periodicity? All I need to know is how long it takes for said observation to come back around based on the cyclical nature of the sky? Are you saying that all I need is actually the periodicity and not the constant? Wow, well, how would I use just an observation like that to predict eclipses?
For example, to do eclipses, there are sort of three numbers we need to know. And basically, there are three different kinds of months. And they come from the way that the moon goes around the Earth. You could measure the time from the new moon to the new moon. In other words, when does the moon actually line up with the same position that the sun is in going around the heavens? When do they line up? That's called the synodic month. That's a $10 word for a 1-cent concept. And that actually works out to be 29 and a half days. But of course, the more accurate your watch is, you get a much better number, okay? So that's one number we need to know. Another number we need to know is another $5 word called the perigee. That's when the moon is closest to the Earth in its orbit. And we can tell that by the size of the moon. The closer it is, the bigger it looks. So we can actually time.
Pay attention to that, because when I'm going to be doing the differences after this in a moment, he's deducing the distance that the moon is from the Earth based on the apparent lunar disk size. Meaning if it was traveling from tropic to tropic and changing its apparent size to us as it goes further and nearer, he's basing the distance off of that. Okay, that's what he's saying.
Time that month. And it turns out that that month is quite a bit shorter, 27 and a half days. And this is something, again, that you can measure in the privacy of your own bed.
And just the fact that they're different, just so we understand, 27 and a half versus 28 and a half versus 29. If the moon and the sun are both orbiting, right, or both going around, if the moon does a complete circuit, but it's trying to catch the sun, it also has to go a little bit slower, a little bit faster to match the speed of the sun. That's why it dips in valleys between 28 and 29. That's how you get 27. Right?
Backyard. For us, it's important to think of a third kind of month. And that's because we want the moon to come between the Earth and the sun, a common plane, a common flat sheet. Well, don't they? No, they don't. As it turns out, the orbit of the moon, the moon's orbital plane, doesn't line up with the Earth-Sun plane. It's actually angled by about 5 degrees. So they don't line up. So it is only when the moon is in this area where those two planes cross, something called a node. That's what this is right here. This is a node. It's only when the moon is close to one of those that we have an eclipse. Well, as it turns out, to have an eclipse, there's a little interval that is about 34 degrees wide. So that's the angle in the sky, how wide it is. It's about 34 degrees wide, where if the moon happens to be in that 34 degrees when the sun is there, you get an eclipse, okay? So the question is, how long does the sun lie in there as we travel around it and look at it out in the sky? Well, the sun moves about 1 degree a day. So to go through what's called an eclipse season, it takes about 34 days for the sun to go through it. Well, the moon goes around in 27, so every eclipse season, you're going to have at least one eclipse in there. You might have two if the moon goes through here. Only one, of course, if the moon is real close to the node. So this tells us that every year, every eclipse season, there are always two eclipses. Always. Somewhere on the Earth, you can see an eclipse twice a year. Okay? Eclipses are actually quite common. There can be as many as 7 in a given year. It just depends on the relative geometry. These are the tones of the moon, if you will. These are the 3 notes the moon is making.
Right, back to harmony, harmonics, tidal constituents.
Well, they have a rough least common multiple. In other words, if I take 223 new moons, 242 node moons, 239 perigee moons, well, son of a gun, that works out to be the same number of days and almost the same number of hours for all of those 3 multiples. I've multiplied it out for you here. 6,585 days, 7 hours, 43 minutes in the case of the new moons to the new moons. About 5 hours longer for the perigees to perigee. Well, what does that tell us? That tells us every 18 years, 11 days, and 8 hours, an eclipse very similar to the one that we just witnessed is going to occur in roughly the same place. What does the 8 hours tell us? That says it's going to be moved 1/3 of the way around the Earth, because 24 hours in a day. So that means that every 3 of those, or 1 excelligimus, okay, which is 54 years and 34 days, we're going to have an eclipse virtually identical to the one that we just witnessed, only twisted a little bit further north or a little bit further south, whether on this is a descending node where things are going down or an ascending node where things are going up.
All right, so that's my buddy Steve, who's a heliocentric lad with no agenda, just interpreting the celestial phenomenon through his interpretive framework and giving us what he thinks. I think that was very refreshing, right? We didn't get called retarded. He didn't try to frame it or obfuscate. Didn't try to change all the details of what he believes to be opposed to us. No, he just told me exactly the same thing as I told you guys. I think the only thing that we would even bicker about is the interpretation of those three different lunar periodicities. But essentially, he's talking about the same thing, right? A Saros, as we saw, what NASA breaks down, is the same cycle. Let me see here. Right, so 18.03 years, which is the synchronizing of all three of these, right? 223 synodic months, 241 draconic months, 239 anomalistic months. So, as he called
You
it.
mean I don't know gravity now?
Isn't that crazy? And he said all you need is a stick in your yard and a watch, and you can predict eclipses.
Shout out to Heliocentric C, Steve. What a homie.
That anyone could do it with the math of grade school, yeah. So all this hip hype that you need Newton and only the globe can do it, and this special book that I bought, and it has the secret sauce that can only be like, no, nonsense. It's, if you're paying attention, right, we're in the realm of kinematics, observation, and periodicities only. But so if we bring it to how we would describe those three different periodicities, right? So he calls them what do you call them? New moons to nodes to perigees. He just named them what they are, right? So those are all different types of months. Now, new moon to new moon, right? That's one that I think we have a better explanation for. So this right here is the synodic month, and this is the flat Earth interpretation of that, right? As the moon goes around and chases the sun, the closer it gets, the least luminous it becomes. As it catches up, that's the new moon. As it passes again, it starts to wax again, right? So the luminosity increases direct proximity with the sun. So as it gets further away from the sun, it gets brighter. The full moon is when it's at its furthest point from the sun. So that cycle certainly goes both ways. It can be interpreted from either model, right? The synodic month, the lunar phase, specifically coinciding with the perigee and with the position of the sun and the moon. Now, onto the node, right? The time it takes for the node, well, that one's super easy. If the moon is making a circuit and it has, solstice, equinox, and lunar nodes, that's just the time it takes for it to go from this node round to this node again. That's all that is. And then perigee, which would be the closest point on its elliptical orbit, would just be a similar thing. It would be the exact position over here. If this is the position closest to Earth's center, then as it goes around, then it'll be back to this position. And those are the three lunar periodicities. So there's nothing heliocentric exclusive in there. What people like McToon like to say is, well, it depends on the 3D moon sun syzygy needs to be heliocentric. And no, what it depends on, as I just said, and as our buddy Steve corroborated, is those three lunar periodicities, which can be interpreted easily by us, right? The moon's close to the sun, the moon crosses a specific point in its node, the moon crosses a specific point in its slightly elliptical, more circular orbit. Boom. Did NASA really come up with that? As we're going to see in just a minute. No. And actually, they attribute it all to our boy Fred Espenak over here. We're going to sail through. Who the hell is Fred? Well, Fred doesn't really work for NASA. He did some consignment work, and he traveled the world, and he went to visit all the ancient cultures, and he pretty much pulled from all the ancient works of all the old cycles and cyclical nature, things like the Antikythera, things like the lunar and the old school Metonic cycles and the old calendars, and he came up with his 5 millennium canon of solar eclipses, with which he essentially just stole an older canon and added a little bit in the beginning and a little bit at the end to round it out. But what he's famous for is this: the 5 millennium canons of solar eclipses. Now, most notably, it's separated into solar and lunar eclipses. Now, there's no reason why you would separate these, as we have been showing, right? They align cyclically and they keep occurring. There's no need to separate solar and lunar unless you're trying to divide people from being able to identify the pattern that comes out in the cycle. So NASA's official website, if you actually go there, will cite Fred Espenak. They will take zero responsibility for eclipses, eclipse predictions, eclipse 3D modeling. They will lay it all on Fred. Fred did all of these, and because of Fred, they have this. Now, what Fred pulled from, and in fact what he references, something called the Canon of Eclipses, which is published in 1887.
What are our taxes going for? This guy's doing it for free. and NASA just points at him. What are we paying the people at NASA to do? What if this guy's wrong? Like, are they double checking his work?
Well, I think we paid NASA to pay Fred.
To pay Fred? Okay. Okay.
Technically, we paid Fred. Yeah, you're right. Fred has his website you can go to buy his books, his atlases, his solar eclipse photographs, plaques, predictions, maps. He's got the whole thing, the whole shebang. But again, if you look into it, he's even referenced this particular work, this canon of eclipses, 1887 in the Imperial Academy of Sciences. Now, occurs in this order. So here's a team of 70 eclipses, right? And they occur in this order every time. So here's the key. This picture looks like a solar. That's a total solar. This is a partial solar. This is a total lunar. This is a partial lunar. So for a team of 70, they occur in this order, and then this order repeats each and every time. So they have a solar.
That's amazing.
Right? This is the part I couldn't get over. So total solar, partial lunar, total solar, total lunar, partial solar, all around we go. And that cycle repeats. And here's how it looks if you were to historically date it. So again, here's a team of 18 appearing graphed out. And on the outside, we can see he picked two random Saroses and he lined them up. So here's Saros 9, here's Saros 10. And again, you have the same sort of eclipse happening in the same order, under the same Saros, for the same conditions all the way through. And that continues to happen, right? So we got total, the same sort of characteristics occurring. So total solar. If you picked up over here, it turns, from solar, total lunar, to partial lunar, total lunar, partial solar, total lunar, because in each character you get 1,260 eclipses if they were to repeat, right? And if you were to take that whole cycle and to just line it up every time, like here's the 44th, same type, total lunar, total partial, all the way through, and each star cycle is indicative of this repeating cycle within it. So the character and type of eclipses is repeated within this 70 eclipse cycle. So to give us a visualization of how that occurs in the heavens, right? You have this one eclipse occur here. Remember, the stars are rotating. So then that eclipse occurs over here 18 years later, and then over here, then over here, then over here, and here, all the way around 36 times to give us one half of that cycle. So when you get two of these, then you get 2,520 eclipses, which is how we get the giant cycle. And of course, again, to visualize, the same eclipse occurs every 18 years for a total of 36 times within 651 years. And that gives you the greater astronomical year, or the greater astronomical cycle of 2,520 eclipses.
It makes you gay.
Super gay if you guys got an astronomical year.
Dude, that blew me away. I had no clue. I had never heard that before.
Right, if you were to think about it, they occur like this around the world. But then if you were to think about how the stars move, right, and how the zodiac progresses, then it would be like this. They would move like this. It would be just processing around, right? So as the stars process, then this eclipse cycle would process. And that's how we get the interconnecting, oscillating cycle.